Hi, and welcome to this continuation of. Hi, and welcome to this lecture. I believe it's 24. All right, so hello and welcome to this class where we continue about the Riesz representation theorem. So it assumes that you have read the book up until 7 to 8, basically. All right, so what do we want to prove? We want to do the first version of the Riesz representation theorem, which says that if I is a linear functional on a locally compact outdoor space X. Okay, sorry. Of course, the linear function is not on X itself, but on the continuous functions with compact support on X with values in R, which is positive in the sense that the value is non-negative whenever the function is non-negative. Then there exists a unique regular Borel measure mu on X such that the functional is just integration against mu. Now, what means regular? Let us remind ourselves, okay, we have these two conditions, and here we put U, which is an open set. So for all open sets, you can do the supremum over mu of K, where K is a compact set included in U. Regularity in RB, you could put here any set A. Remember theorem 1.5.6. And here on the lower line, you have any Borel set A, and then you can also do the infimum of open sets, including A. Why can't we do A here? Well, actually, it beats me. Proposition 7.2.6 tells you that this is true as long as X is a sigma finite space, or more generally, for any set A in X, which is sigma finite, you can put here A instead of U. So this seems to be, I don't know of any relevant examples where the space is not sigma finite. But okay, there is this distinction, which in very big spaces does some change. Okay. Now, getting to the proof of this theory, we have to first think, all right, so how we sit here with this functional I, how would we go on about constructing a linear functional constructing this measure mu. And then just to get the idea, what you have to do then is, of course, you have to assume that you have this representation and then say, okay, how do I get my measure mu using I? Well, the most natural idea, which we did when we did, we had a similar problem when we did duality theory for LP, LQ. In that case, we just defined mu of a set A as the functional I applied to the characteristic function of A. And like that, we got a measure. Then the big problem there was to prove that actually that measure is absolutely continuous with respect to some predefined measure mu. And then we could, because they were one functions in the duality theory, LP dual is a function space LQ. Here the situation is a bit different. We just want to show that the dual is a measure can be represented by a measure, sort of linear functional. So we want to find this guy mu. But we're not allowed to use him because remember.
Okay, sorry. Of course, the linear function is not on X itself, but on the continuous functions with compact support on X.
And that's not a continuous function, right? So what can we do then? Okay. Here is our guy A. But clearly we have two choices here. We can either look at functions which are below this characteristic function and then let them become closer and closer. So a natural attempt to define this mu of A would be mu of A is equal to the supremum I of f, where 0 is less than f, is less than characteristic function of A. Now, this definition leads to a problem, which probably kind of gives a hint to why things are like they are here with the open sets. Because imagine now if we want to realign and A is the Cantor set, it has no interior. Yeah, there doesn't exist one single interval in it. Yet we have measures who live on the Cantor set, which give you continuous linear functionals. So if A is the Cantor set and mu is a measure that lives on the Cantor set, then this could be a non-trivial linear functional defined like this. But this definition here would just give you 0 because all the functions f with compact support inside the compact in the Cantor set must be identically 0 if they're going to be continuous. So that's why we have to make this a nice set for this to work. So then we do here that, okay, we do the definition only for open sets, because then any point in open set has a small neighborhood. So we know that if this is a point, is a member of my set U, then I can find a small interval around it, and I can always do something continuous in that neighborhood, right? Using these results from what I discussed last time. So there exists always a function which is 1 in this point and 0 on the complement of the open neighborhood, right? So that's a closed set, and the point is also a closed set, right? So we can find functions like this. Right, so then we define it like this, and once we have that, we're going to define u of A as the infimum u of U or U open, like we want in the regularity. So this makes a lot of sense, because now if A is a difficult set, Cantor set, whatever, then still, you can always take open sets around it, which are very tight, so to speak. Yeah. So this would be the definition. Why we didn't flip this around and started with mu of A equal to infimum I of F, where we just simply had that characteristic function of A is less than or equal to F. Because that would be somehow the natural point of view if we start from here instead, right? Wait. Yeah, no. Yeah. Okay, I don't have a good answer. I'm just pointing out that it's not 100% clear here, but apparently this leads to some sort of complication. One could be that the support of your functions f is always closed, so this has no relationship with the open set really in the regularity. You want open set here. Okay, so this is not the way to do it. All right, now that we've figured out how to do it, we just have to wade through the muddy details, and unfortunately that gets tricky again. Yeah, so the proof starts out defining these things, and then we have to show. So now this definition, it works actually for all sets A, right? But so how do we prove it's a measure? We prove that it is an outer measure. Yes, and I can put maybe a star here as well. So checking outer measurability is easier. Once we have that, then we need to check, okay, then we know that every outer measure defines a measure on the set of measurable sets. And then we just have to check, and we know also that that's a sigma algebra, so we just need to check that that sigma algebra is bigger than the Borel, meaning we have to check that every open set is measurable. I will leave the details of that to you. It's all in the book. All right, I changed my mind. The details of the proof are actually nice. I mean, we still have to, okay, this is how we set it up, but it's still very interesting to see how we get to this formula. So the details of how you check that mu star is, you know, what I just said is an outer measure under the Borel open sets or mu star measurable and whatever. That I will skip. It's a lot like repeating arguments from 1.5. But once we have all of that, we have to prove this key formula, right? That the linear functional and the integration gives the same result. So here we need a key. So there's a proposition or a lemma which says that if you have the characteristic function from Borel set A, and that should also be compact, please, that simplifies the argument, but it's not necessary, it's written in the book. But anyway, I'll do that. So let's say we have this situation, and then we want to know first that mu of A is less than or equal to I of F less than or equal to mu of B, which, you know, if you think of this as integration against mu is pretty obvious, right? And also kind of easy from how we define things, right? Because if this is my set A and this is my set B, then these conditions there says that, well, it goes up and then it stays 1 on A, and then it goes down and it's 0 outside of B. So clearly integrating this, yeah, you just, well, F is between these characteristic functions, you just throw in the characteristic functions and then you get this from the integral. Okay, so how can we prove this? Figure is inverse to be compact. Well, I'll tell you at the end of the proof which one needs to be compact. All right, so let's start with this one. Then, so how do I define the measure of any A? Well, it's an infimum, right? Of the measure of open sets, and that is then in turn connected with integration, with the linear functional. So I have a function f, well, maybe I look at all functions f. No, this is a concrete function f that does this. And then, well, if I just look at the set where f is bigger than 1, I might get a void set. Bigger than or equal to 1, I get a closed set, and we don't want that because we want to work with open sets. Yeah, this is the infimum of open sets. So how do I get an open set connected with my f? Well, I look at the point 1 minus epsilon, cut through this and project it down on the axis here. Then I get a set that's called u epsilon, which is bigger than or equal to A. Now, we want then the measure of mu epsilon to be more or less this number, right? We want to connect those two. So what is the measure of mu epsilon? Sorry, of u epsilon. It is the supremum I of G, where G is less than the characteristic function of u epsilon. Now, to connect this with something that has to do with I of F, we need to do some inequality like this between G and F, but we don't have that. Because the only thing we know about I is that it is non-negative. So it somehow respects bigger than or equal to. However, if I just boost F a little bit bigger so that it rises up. Okay, so where are we? So the function G, let me paint him in green, is somewhere here, right? But he goes up to 1, and it stays 1, and then he goes down. So I mean, the G could actually overshoot the F a little bit here once you're outside of A. And that's the problem. But we know that G is less than 1 inside of this U epsilon. So if I could just make F bigger than 1 on that set, then I'm fine. No, F isn't that, but F is close to it because we know that it's bigger than 1 minus epsilon. So what we have is that G is less than 1 over 1 minus epsilon F. So this lifts up F up a bit so that we have this, right? So this supremum here is less than or equal to I 1 over 1 minus epsilon F. This is a linear function, so this can be pulled out, and then epsilon can be made as small as we want. So at the end of the day, you get U of, right, we get U of A is less than or equal to U of mu epsilon. Now this in by itself is not less than I of F, but let's do it like this, infimum here over all epsilons, and then you see that this is less than or equal to I of F. So that's what we wanted to conclude, right? Because for each epsilon, this is less than this, and then epsilon goes to 0, so the infimum will be I of F. Right? So then we establish this guy, and to establish this fellow here is even easier. No, I don't see why we need any one of them to be compact. Anyways, I'm not going to get worried with that. But anyway, so mu of, no, it beats me. Okay, so here we have some complications. B is not necessarily open. If B was open, then this identity holds by definition again, right? Because this is how we define the measure for open sets. So now, if you want to prove the second one, you can pick. So for all epsilon, you can pick a U epsilon. Wait, so here we need regularity, right? Exactly. So we don't need to worry with epsilon, but if U is an open set bigger than A, then we have that F is less than or equal to the characteristic function of U. So by definition, then U of U is bigger than or equal to I of F, right? And this happens for all U's. If I now take an infimum over all possible U's, then my regularity of my new measure, wait, by definition, that's how we define it. Yeah. Okay, so I don't see, wait, here should be the B. By definition of the measure B, mu of B is bigger than that. Okay, well, anyways, so nice. Now we have these inequalities, and now how do we get to the key formula we're chasing here, which is that we write it again, I of F equals to integral F in mu. Well, if F has a positive and negative part, this is linear, this is linear, so we just assume that F is non-negative to begin with, and then we can paint it something like this. This picture is also in the book. Yeah, and here what we're going to do is we're going to chop this guy up. So this first set, I think is going to be K1. Yeah, because the first set is K0. Let me write it here. So K1, K0 is the full set, the other endpoint. And then here is K2, right? You get my point. And K3 will be a bit funny because we'll have a piece here and a piece there, right? So these sets are by no means necessarily simple, but they're going to be close. Okay, well, I forgot. So, and then what you want here is that the height here is always epsilon. So here you have 2 epsilon and so on. So to construct this function, write it up in the book. The definition looks a bit like you have to look at it, but it's only this. So right. So what they do is, let me paint this. So you get this sequence of functions where f0 is the minimum of the function f and the characteristic function of this compact set here. And then, so this is f0 or f1, I have to check, but it doesn't matter where you start counting really. And then f2 is going to be living on k1, okay? And it's going to be precisely what you get from chopping out this section here. It's just that we shift it down so that it always, it has compact support. We don't have a jump discontinuity here. So you create these functions such that your function f is equal to a finite sum, but we don't know how high it goes. Maybe I should have it. I can just put infinity there. Doesn't matter because they're all 0 function after a while. And all right, so and we have this, right? Hi, so this is just a heads up that I will change this indexing at some point. Of course, indexing isn't all that important. You can start at 0 or at 1 or wherever. But in the book, they start at F1, which I called F0, which means that this inequality I just wrote up, it will be xk, sorry, it will be kk to the left, then fk, and kk minus 1 to the right instead. Just a tiny, okay, I'll tell you now so you don't get confused. Well, anyway, that's the intention. Maybe it doesn't go all the way, but in Sweden there's some saying that it's the intention that counts. So f0 is less than the characteristic function of k0 times epsilon. Yeah, this height is epsilon still, and is bigger than characteristic function of the smaller guy, because here it is identity 1, so identity epsilon. Okay. So this is a bit like doing Riemann integration. Of course, the idea here in the end is that the linear functional applied to f is equal to summing the linear function applied to your fk's, and that's going to be approximately equal to summing epsilon mu kk, which is approximately in turn equal to integrating f mu, because once you have a sum like this, it's like you integrate characteristics, right? So you just replace what you have with a function like this. Yeah, that would be this one here. Can you see that? Okay, so now to do this formally, what we have, of course, is that f is locked in between epsilon times the sum characteristic function of k, let it change index here, kj, j going from 0 to infinity. So that will be this outer guy, right? And similarly, we have an inner guy. where instead of starting at 0, we start at 1. Yeah, so then you get this fellow, sup, 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 and so on, right? Sitting below. Right, so if we now integrate these three guys, we get an inequality which says epsilon times sum starting at 1, measure kj less than or equal to integral f less than or equal to epsilon, and then sum starting at 0, mu kj. All right. So these sums actually are the same sum, right? Except that here one has to be a bit careful. This sum should actually not go to infinity. Or should it? Yeah, I think it's fine. Because at some, in the book they fiddle with the last and the first set, but I don't see a problem with that. So basically, this sum and that sum are the same except for the first ingredient. So meaning that the difference between him and him is less than or equal to epsilon times mu of k0. And this is some fixed finite number, and epsilon can be made as small as 1, right? So these numbers are pretty damn close to him. Now, right, so now we want the same inequality for the linear functional. And what we do then is now need this type of lemma, right? Because each fj satisfies such an inequality where here you have the kj minus 1 and here you have the kj, right? See here. So playing with that, we see that each so epsilon u of kj minus 1 less than or equal to I applied to fk less than or equal to epsilon u kj, right? And now if we sum up all these guys, we get I of f, right? And then if I sum here, I get a sum. Rewind. Here should have been a j. And of course, the inequalities go the other way. But let me keep them like this, and here write the -1 and erase him here. All right, fine. This is what I wanted to have written. Okay, so we have this, and now we sum up. So we sum all of these guys, use this formula, and we get I of f. Sum up all of these guys. Of course, we start at 0. Sorry, we start slowly. Right, so the numbering was important. This guy is the one we should call F1, this is the one we should call F2, and so on. Then this thing holds now with the proper indexing. So then to get back F via this formula here, we start summing from j equals to 1. And then here we get, well, basically we get this guy, and then we get less than or equal to I of f, and less than or equal to this guy, right? So the integral of f and I of f, they're locked in between this number and that number, and the distance between these two numbers is something that go to 0 as epsilon goes to 0. So this value and that value needs to be the same. Beautiful, right? Okay, so I have to erase the blackboard. Well, let me do that first, and then I come back. Right, so while the other two blackboards dry out, I can do a bit of talking. So now we come to chapter 7.3. And actually, a lot of it you know already. So it's it starts out talking about this case C0, which is all continuous functions that vanish at infinity on the locally compact space X. And I discussed that in a previous lecture. So this is then, the K of X is a subset of that. And in fact, this is a dense subset. This is a Banach space. And yada, yada. There's nothing complicated there. So he establishes that first. Then now we're going to start looking at the dual of him, right? So we're interested in this. And we want to say that this is all the measures on X with values either in R or in C. So then all the regular measures, okay? And then we want to prove that this is a Banach space by itself, it has a norm and so on. So to warm up to that, it starts with some inequalities related to the variation of the measure mu, which is defined exactly as we did it in chapter 4. And yeah, so this is about as interesting as driving through Kansas or something. And then finally we reach, he has a few regularity results also, how you can approximate measure mu being regular. And then we finally arrive at the statement, which is that, well, basically this, yeah, so the dual of this Banach space here is this Banach space here. So any either finite sign measure, so duality could either be complex dual or real dual. Your real Banach space, if you look at real valued functions, then you want your linear functional means linear over R, meaning you can pull out constants that are real values. Complex linearity works exactly the same, it's just that now you allow complex numbers, complex functions, and then you get complex measures here, which we know what it is, right? It's just the sum of two finite sign measures, which in itself is a sum of two non-negative measures. Okay. Question then is, how do we prove this result? So somehow we're not going to repeat the proof of, we have the result already for, if we have a bounded or not, if we have a linear function here, which is non-negative, then we know it's can be represented by a measure by the theorem I just erased. So how do we use that to establish this result? So let me just do it for the case where we have reals, because the complex situation doesn't offer any additional difficulty. Right, so the interesting part here is that for some reason it's now called the function as L, but I'll stick with I. So if you have a linear function of I on the dual of this guy, then you want to write I as the difference between a positive and a negative linear functional, or non-negative and non-positive, which I hate terminology. All right, so the interesting thing is, how do we construct this? There are many other things you have to check in the proof that, so each measure which is regular gives linear functional, that's pretty obvious, but then and then you only also check that the norm of the measure is the same as the norm of the linear functional. There is some yada yada going on with doing that. I'll just skip that part, because this is then the interesting part, which is what you need for surjectivity, which is to say that for every linear functional, I can find a measure mu which represents it, and then, armed with what we already have, I just need to prove this decomposition here, where this is a non-negative guy and he is a non-negative guy. So then, all right, so let's, it's a bit hard to, but let's think of, so here's the space X, right? And then this is the positive part in the Hahn decomposition, and this is the negative part of the Hahn decomposition of the measure mu, which generates this functional that we haven't established yet that it exists, but we can think of it as existing. So what is then I plus? Well, it is of course integration against the positive part of this measure in the Jordan decomposition. So integration here, right? So if I now take a function f like this, and I want to figure out what is I plus of f, well, I don't want any of this to count, right? And I want all of this to count. So if I knew where was p, I would just take a cutoff and consider like this piece of f here. Yeah, but I don't know. First of all, I'm not allowed to do cutoffs because then I'm leaving continuous functions. And second of all, I do not know where is my p. But clearly, all right, so we can do something like this. We can consider a function g, which is below f, which has the support in p. Then the integration of g will be like integrating f against the positive part. This measure use, we will have in the end integration f then u plus is approximately equal to integral of g, as long as g stays in here, but we don't know where is p. Well, then let's just define I plus of f as the supremum I of g, where g is less than or equal to f and bigger than 0. Well, I think this is not necessary because otherwise, well, no, yeah, we want them. All right, because otherwise, if this has negative part, we cannot negative times negative is positive. So, right, so then g could actually have a blob here, right? But that just works against our supremum. Now we get got smaller numbers, and naturally the supremum will be attained for g whose support tends to kind of accumulate in p. So this is a logical definition to make, right? Once we have this, we just have to establish, first of all, that I plus is linear. And then we have to establish that I minus I plus, we define that as our I minus. No, I plus minus I, this will be our I minus, right? Then we get the cancellations, right? We need to check that this is bigger than or equal to 0. This is not a big deal, but linearity is a bit fishy. The details are in the book, but so somehow, all right. So if I have, here's my F1, here's my F2, and now what I want to do is I want to prove that I plus applied to F1 plus F2 is equal to I plus of F1 plus I plus F2. This is the difficult part, right? And then, all right, so we don't know where, all right, let's say that a G that almost attains the supremum for this F1 is this guy here. And then a G that almost attains the supremum for the other guy is this guy here, G2. So then I applied to him, and him will be close to this value. But then you see that, okay, so now G1 plus G2 is less than or equal to F1 plus F2. So like that, we easily get right, we get that I plus of F1 plus I plus of F2, which we can get arbitrarily close to by considering I of G plus I of G1 plus I of G2, and then that is less than or equal to I plus F1 plus F2, right? And now for the reverse inequality, okay, here's written F1. Okay, so what is the sum here? So F1 plus F2, if we want to paint it, it looks like this. And then here it has a bit of a bump, and then it goes down again. So if with this definition we have, I want to get close now to this number, I just take a red guy, G1, let's say, actually the positive set is somewhere here in the middle, and then, you know, maybe this is my, you know, G that gets close. So I of G is close to that number. Now the problem is that G is not below F1, it's not below F2. So what we then do is to consider the maximum of G and F1, and suddenly we have a function which is below F1, and then you consider the function G minus what you created, so somehow the function, you know, under this piece here, and now you have a G1 and a G2, and then you establish the reverse inequality. So that's it for that. And I would say more or less that's it for the entire chapter. So I tried to look for something interesting in the remaining material, and I failed. Well, interesting it is maybe, but definitely not on the first reading as a student. You don't want to waste time here. So it's good to know that it exists. I'll tell you what's in there briefly. So, well, no, you can read the titles yourselves, but it's nothing that I ever use. But every now and then in mathematics, there's especially in the older days, there were some people coming from this like Bourbaki school, which is some French kind of thing. And they had a different approach to measure theory. Bourbaki was some sort of French general then there was a whole group of French mathematicians who published under the name Bourbaki because they, I don't know, mocking the guy or whatever. So anyways, so this Bourbaki approach to integration actually flips the whole story around. So it starts with just linear functionals on spaces of continuous functions with compact support. And then kind of, yeah, so it doesn't work with measures, it works with linear functionals, so basically things here. And yeah, so it starts at the other end of Riesz representation theorem and somehow builds up a whole integration theory around it. So the measures come in later or don't come in at all. But anyways, you can work out then that the approach taken by Bourbaki, where just measure is a linear functional on continuous functions with compact support, is the same as what we have arrived at here, right? So if you have the measure theory, Lebesgue integration framework or the Bourbaki framework, they are equivalent. That's very nice. They come to this conclusion in, now I have to check. Right, so talk about this at the end of section 7.5. So 7.4 is more stuff about regularity. I think you know everything you need to know about regularity already, but this more locally compact of those spaces. And then in 7.5, then again, all right, now you can define L1 against the measure on a locally compact regular Hausdorff space. No, not regular Hausdorff space. And then, right, then you want to develop the theory there that the dual is somehow L infinity, blah, blah. And there is where this Bourbaki integration theory comes in. And then there is apparently, that I've never heard of in my entire life, a Stone-McShane approach to integration theory, which to me on the surface looks very similar to the Bourbaki one. It's just the axiomatic treatment of which functions. So you start with linear functionals, and then you have to work on a set of functions that somehow your linear functionals apply to, and then there's some difference there with how the Bourbaki guys set it up, and they devote a chapter to that as well. Bottom line is, at the end of the day, they're all the same, with some extremely tiny variations possibly. So, and I think this approach to measure theory that we are teaching here is somehow the winner in the end. So, I mean, you be the judge after reading 7.5 and 7.6, but I find the other. I mean, this, okay, measures, sigma, algebras, yada yada. It's complicated, but once you get used to it, somehow it feels natural. Maybe it's just the way, because that's the way I learned it. But this other way, this axiomatic treatment of, I don't like it. Anyways, that's the end of chapter 7. Chapter 8, I glanced through it also to find something useful. I mean, we did use it at some point, right? So it studies Borel sets and also like what, I mean, so we said the whole time, okay, so sets can be very complicated and we don't know exactly how they look like. But then at some point, we managed to prove that Borel sets are actually infinite unions of, you know, this F sigmas and the G deltas, which are either infinite intersections of open sets or infinite unions of closed sets. But then you start iterating this process on these, you flip back and forth. And if you do that to infinity, you can actually construct all the Borel sets. But I guess it's a very natural topic at some point to study. All right, so can we somehow characterize what does it mean to be a Borel set? And then Rn is not the ideal environment. The ideal environment is locally compact Hausdorff spaces. And that's why this comes here. So it's called Polish spaces, because apparently some Polish and Russian guys in the in-between war period there in the 20s and 30s, they worked out all of this stuff. And yeah, I'm sure it's beautiful mathematics and all of that, but in terms of usefulness, I find very little there, right? So yeah, I'm not going to say too much about it. They have this concept of analytic sets. So I mean, what is a nice set, so to speak? Well, Borel sets are then nice. We have somehow been able to construct them now. And then you can ask questions like, okay, if I send a Borel set forward through a continuous function, you know, whatever, what kind of set do I get then? Is it still a Borel set and blah, blah, blah? And apparently not, but you can always squeeze it in between two Borel sets. Yeah. Anyways, so that's that kind of flavor of results is what we do in chapter 8. Next lecture is about chapter 9, hard measures. Sorry. Yes, hard measures, and that is actually a very useful topic. I've seen it appear over and over again in research literature, so it's very good to know what those measures are. So see you next time, and that's all for me today. Thank you.